Okay, so welcome back. Let's see. So this is the second part of the chapter 5, resampling methods. In this video, we are going to talk about bootstrapping. So Bootstrap is a very useful method for resampling. The good thing about Bootstrap is that it doesn't involve like a very complicated mathematical calculations. The whole idea for Bootstrap random sampling methods is to basically use the existing sample sets by drawing random sampling from the sample with replacements so that we can create a new sample data set with the original data set. It has many applications to this bootstrap analysis. For example, we can use a bootstrap to basically create a new set of data and train our model and trying to test out the trained mean square error to see if it's in line with the original data set. Or we can actually estimate the standard error for the coefficients, or maybe even we can create like a different R square with the bootstrapped data sets to check if the model specifications actually provide the consistent R square results. So in general, the whole idea for Bootstrap, it's basically required two steps. Number one, we basically need to create a function that computes the statistics, like the standard error for the coefficients, or maybe the R square, or maybe some other use of the equations, like means, values, or maybe standard error, standard deviations, variance. So any functions that we calculate the statistics. And the second step will be using the boot functions in R to basically perform the bootstrap by repeating the sampling observations from the data set with replacement. So that's basically the overall. So let's take a look at the exercise today and try to understand a little bit more of the procedures to perform the bootstraps analysis. So today we are going to use the portfolio data sets. So if you don't know what it is, obviously you can basically take a look. The portfolio data set, it's pretty simple. It has only two columns of data. You can actually get X and Y column. So the X basically is the column that represent the return from SSX. Y is basically the column represent the return for SSY. So the general idea is this data set will provide us 100 observations about the return from X and Y investments. We want to know which the assets we should actually put in our money to invest in order to avoid the lowest variance of the return to find the total returns from the two. So the whole idea for today's exercise is to find out if you have, like, let's say $100 in your pockets right now. So you want to actually think about whether to invest to SSX or SSY or combinations of the two. What would be the ratio? Should it be like 100% on X, 100% on Y, or maybe 50% on X, 50% on Y, or maybe different ratios of your money should be devoted on this investments. So in order to calculate the variations of the return from X and Y, there is an equations in your textbook, which is from section 5.2 that talks about this alpha functions. So I'm just going to basically put in this alpha functions here that yields the returns of SSX and Y combined. So we're using the variance of Y minus the covariance of X and Y divided by the variance of X plus the variance of Y and minus 2 times the covariance of X and Y. So for people who are a little bit more backgrounds in finance, you probably see this, you have seen this equations in your very fundamental finance classes. This is basically the portfolio analysis if you're giving two assets on hand. So we're going to store this alpha functions first. And what we're trying to do is basically using the Bootstrap's methods to find out what would be the combinations of investment X and Y should we put in our money to buy. So the way how we use the bootstraps, it's pretty simple. So we just need to remind ourselves we have load in this boot library. So let me just copy and paste it down here so that we can remind ourselves that we are using this library. So let me just put this here. So we are going to run this boot library. So in order to calculate the alpha functions, you basically you can use the whole data set X and Y, right? You put in the two columns, and then you basically tell the alpha functions to basically test on the observation from row 1 to 100. So let's see. So as you can see, the alpha functions here returns to you that the standard error for the alpha is 0.5758. So basically, this is the standard error for the investments between for the X and Y. How much variations you will get returned from your portfolios. So you want to actually minimize it, right? So you want to actually see how the portfolio can do better, like without knowing about how much you are going to invest on X and Y. You want to know what is the combination that yields the lowest variations, right? So sometimes if you are involved with an investment, sometimes that yields you with a negative return, and sometimes with positive return, sometimes zero return. You want to try to minimize the variations. You want to find the combinations of X and Y that yields maybe most of the time that will be on the positive side. So in this exercise, we will first set the random seed for our random sampling. And what happened is we are going to do a random sample from 1 to 100s. We pick 100s, and we are going to do it with replacements. So let's see what we are going to do here. So this is basically kind of like a bootstrap style, because we are setting the random sampling with replacement here now, but we are only doing it one time. So let's see. So once we are shuffling our data sets, right? So we are picking basically X and Y from 100 rows in our data set, but there is a possibility that we might actually pick something for 2 times or 3 times to fill in our samples. So this alpha function basically is taking a random sample set from our sample with replacements and trying to calculate the variations from your investments profiles. And in this case, the variation is getting bigger. So as you can see here, so it becomes 0.7368. So now it gives you an idea. So if you are going to invest in X and Y combinations, the initial variations will give you 0.5758 of a variation. So it seems like, well, it's narrower when you actually randomize your samples with replacements. So this one-time bootstrap measurement is going to give you a result very different from your data sets originally suggests. Now let's see, we want to actually try to repeat this Bootstrap random sampling and put it into our alpha functions. So again, what we need to do is to use our Bootstrap functions here, and we're going to put in our sample datasets portfolio, and we define what functions that we want to use to calculate for this particular sample set. So we are trying to find out the variance of returns, these alpha functions here. And we are going to also pass in this parameter called R. So R, it's basically a parameter you can put into the boot functions that define how many times you want to actually repeat this Bootstrap random sampling. So again, if you are not sure about what the boot functions can do, so you can actually ask the help functions here. So as you can see, there is a parameter right here, R, that you can actually put in. So R is the number of Bootstrap replicates. Right? So it can define how many times that you want to draw this random sampling with replacements from your original data set. So in this case, we are trying to draw 1,000 times and trying to average the alpha value here in this calculations. So let's see, after we run this Bootstrap sampling 1,000 times and average the alpha values, the variance, what are we going to get? So we run this, we save it into our outputs. So puts out, and then we print it out. So this Bootstrap functions that we are using here, it's actually a very convenient tool because this Bootstrap analysis will run automatically 1,000 times for this random sampling with replacements. And at the end, this final output will show you the original data, alpha heads that will have a 0.758321. So if you don't do anything, right, so this is the number you're going to get right from your original data sets. So it will also tell you about what is the bias, right? So this is the bias number. So the bias basically tells you, well, how likely you'll be off from your number. And here, the standard error, it's basically the one that we focus on. So the standard error tells you how likely you will get one standard deviation away from your original data set's estimates. So the original data sets tells you that you will have variations of 0.57581. So one standard deviation away is 0.09366,347. So how likely you are going to get a number that it's one standard deviation away? Obviously, it's not that often. You can definitely look back on the t-distributions to see how far the one standard deviations is away. But this output, again, will give you the standard error of this alpha hat, which is the alpha value you get from your data sets. So the Bootstrap approach can also be used in many different ways. So instead of like calculating the variance of your profile returns, right? And you can also use the Bootstrap methods to do a lot of different stuff. So if you are going to print this output right here, so this output will give you the idea. So this is the mean. So this is 0.5758, which is from your dataset's outputs. And there will be many times that you will happen in between this area right here. But sometime you might actually get a number like the second trials that we have. So the second trials, when we trying to do one-time bootstraps, we actually get a random number here, right? So we randomize with replacements. We get a variations at around 0.7368. So rarely happen, but it could happen, and that's the beauty about Bootstrap estimations. So the Bootstrap allow us to do this analysis to see, well, running this 1,000 times, how likely you will get a values in surrounding this mean value, which is your original data sets would suggest. Again, well, you can actually try to run this as many times as you want. For example, if you want to run this 5,000 times, so I define out to be 5,000, I run it, and I print it. As you can see, the first number will still always be the one that we get from our original data set. And now, as we're running a higher frequency here, you are actually seeing that the standard error will be much narrower. Well, this is due to increase in sample size, because we are basically having 5,000 sample sets to calculate the error values. So the more we are randomly selecting from our original data sets, the more likely we are going to hit the same number in the middle. So that's why it becomes more and more central. And the standard error or the standard deviations of this mean distributions will be more narrower. So you can also see the graph right here. So as you run 5,000 times of the sample, right, so it will get shaped into a much narrower distributions. So it will be more central in that middle point. Right, so another good use of Bootstrap is to basically trying to find the standard error of the coefficients. So it's very commonly used in statistics. So for instance, let's say we have a linear model that we want to do. Let's say mileage per gallon predicted by the horsepower. We are going to use the data sets. Probably gonna need to change data equals to auto here. Yes. And we're going to use the subsets, which is index right here. Okay. Oh, data is not data. It is we're creating a function here. So we want to create a functions here. We want to pass in the data here, and we want to pass in the index here. So we want to actually get the coefficients from the model, and then we want to see, well, how are we going to use this? So let's say we save this functions, and we are going to run this boot functions with the auto data set. So we are going to pass in auto to here, and we are going to run this from index 1 to 392. So all the data sets in auto, the 392 rows of data will be passed into this subset. So basically, we're using the whole thing. And let's see. Once we run this, as you can see, it returns the coefficients from the linear model. So the coefficients here, we have the intercept, which is equals to 39.935. And horsepower negative 0.1578. So this is the beta 0 in our linear equations. This is our beta 1 in the linear equation. So we can actually run this. Easily we can retrieve this intercept and coefficients. And now what we want to do is trying to compare it to, let's say, using these functions right here. Just pass in the autos data sets right here. Obviously, we're going to get the same thing, right? Because we're defining subset here, which include all the data, right? So all the numbers. Now, let's say we want to actually use Bootstrap to see, well, how the coefficients, the beta 0 and beta 1 could be different from this number, right? So this is the number that we are going to get when we're using all our data sets. So we want to actually use the Bootstrap methods to resample, the data with replacements, so that we can actually get a different data sets to pass into our model specifications, and trying to estimate this coefficient again. So if we are going to get some different numbers here, then it should be how we expect it, because when we're using a different data set, we should actually generate a very different estimate. So we want to know how much it vary from this estimate from our original model. So again, we set the random seeds right here, and we are going to do the sample functions, right? So we are going to randomly select sample from an index number 392, and we are trying to pick 392 randomly. And this time, we are not picking them independently, and we are picking them independently and with replacement. So what it means is we are going to basically have 392 in our index number. We pick one number out by random, let's say 5, the first time. And then what happened is we are going to put the number 5 back into our original index list, and we are going to randomly select another number. So that means 5 can be picked again. So it's basically the whole idea about Bootstrap. So let's say we save this Bootstrap 1, and we're gonna run the boot functions that we defined earlier, right? So we're trying to get the coefficients by putting in the auto data sets, and this time we are not using exactly 1 to 392. Instead, we are going to put in whatever the random selected index into this functions that will pass into this subset identifier. Right, so this puts S1, the random selected index with replacement, will pass in here. So again, the index number in this boot S1 should have some of the index number repeating itself. So there might be 2 5 and 3 10s, maybe 10 11s, or 5 300s. So because by the nature of this Bootstrap resampling method, you should expect to see some repeated numbers. Before we run that, let me just print this out to see if we get idea what we're getting here. So again, as you can see, well, those are the randomly selected 392 index number with replacements. So you can easily find something like here. So 300s and 300s. So the index of 300s actually happened 2 times, easily found here. And you're probably going to find a lot more of the replicates from this list, like 75 I can easily spot, and 75 right here. So we are going to pass in this index into the subset so that the linear model will run under whatever we define here. So let's see. So we run this, and now what happened is it returns a different coefficient, right? Because, well, the data that we are going to use to train the model is different. So we get an intercept equals to 40.34, and we get a horsepower right here equals to negative 0.1634, compared to the previous results. And you can now find that they are different. And if you are going to do another resampling, right, so exactly the same thing right here. So we're going to do another run. And now we are going to print this. So as you can see, we are going to have a totally different random sample index with replacements. Again, you will find a lot of this repeated number, 4 and 4, right? And maybe something like, I don't know, maybe you can easily find them somewhere around. But there should be some repeated number. All right, so let's say, well, I want to actually find the coefficients again and trying to see, well, whether it will return the same coefficients, the beta 0 and beta 1. Run it again, well, the numbers are different. So 40.11 in this case, comparing to previous 40.34. And beta 1 coefficient is negative 0.157 comparing to 0.163 before. So now you might ask the questions. So why are we doing this? Right? So what's the point for doing this? So the whole point is basically to give you an idea about how you are going to be sampling your data sets to generate new data sets. So once you generate this new data sets, what you can do now, the final steps, so you can actually use the Bootstrap formula or the functions to define what you want to estimate, right? So you can actually now use the boot functions, and you can now pass in this parameter r equals to 1,000 times. So here you have the original data sets to pass into these functions, right? So you get an estimate for your coefficients. You do it a second time with the resampling, with replacements. This is the first time of the resampling, and you use the Bootstrap functions, right? And then you pass it in this new random data set with replacements, and then you do it the second time right here, and you get another estimate of the coefficients to pass in here. Now, doing this by hand, it's very, very slow. So now what you want to do here is to use this Bootstrap function and repeat this step right here, not just one time, 2 times, maybe for 1,000 times. So let's see what we can get from here. So let's save this to boot.lm. Right, so it's from the linear model. So save this, and let's see .lm. And here you go. So you can see that I have two t-score that we returned from this output right here. So the first one right here, 39.935, is the one that we actually get from the very, very original estimates. So we're using all the current data sets to run the model, and that's the average we got. Right? That's the estimate. And then the negative 1.578 right here, it's basically the original coefficients when we're doing the trainings with the original data sets. Now, how we're doing 1,000 times, they will vary with each other. So this is the standard error. So this is the standard error. So one standard deviation away from the means, 39.93 will be 0.8412. And how it vary for the coefficients, beta 1, it will be 0.007 away from the mean value here, 0.157. And if you want to see how well it actually distributes, again, you can definitely plot it. You can plot LM, and here you go. You see that the T, now it's actually very central to this point right here. So the general idea for Bootstrap, again, is to allow people to use this resampling methods to resample as many times as they want, so that they can generate new sample sets again and again, until at some point they can actually say, hey, you know what, I have now 5,000 sample sets, and I would like to get some estimates how much the variations from this estimate from our original data sets. That's basically the main use of the bootstraps. So as you can imagine, this bootstrap method, it's not only limited to get the coefficients standard error, right, like this kind, or maybe getting a standard error of a variance returns, but also it's good for any statistics that we're only getting one time from our outputs. So for instance, like the p-values from the F statistics, or maybe the R square, or maybe even some other more complicated statistics that we are going to talk about later. So keep that in mind. Bootstrap is a very useful piece of statistic tool. You don't need to know the mathematical behind because it generally applied to other statistical methods that we use in this class. So most of the time we can still reuse this methodology to get estimates of the variations. All right, so at this point, I would just say please read the textbook, right? Study from the textbook a little bit more to kind of like getting a concept of this bootstrapped chapters or sections. I hope you enjoyed this video, and I will basically give you guys a little bit more hints on the assignments posted there for you guys to see. So hopefully this will be helpful for you. Okay, so I will see you in the next video to talk about the decision trees. So I will see you guys next time.